I'm going to talk about rotations, including rigid bodies and torques. So let me list some examples of rotating objects, and then we will discuss. Spinning tops, swinging bats, and doors that are opening or closing. Okay, so in a spinning top, all the matter in the top is rotating about a line through the center of the top. Whenever the matter in a system is rotating about a line, we refer to that line as the axis of rotation. Okay, now let's talk about swinging bats. So think about a batter in a baseball game trying to swing a bat to hit a baseball. Now, in that example, there is a vertical axis of rotation approximately through one end of the bat. Okay, the end closest to the batter's hands. So all the matter in the bat is rotating with respect to that vertical axis of rotation. In doors that are opening or closing, in a door that's opening or closing, all the matter in the door is rotating with respect to a vertical axis of rotation through the hinges of the door on one side of the door. Now, if objects are not rotating, to get them rotating about an axis of rotation, you need to apply a force. Now, there's something curious about causing an object to rotate by applying a force. If you apply a force to one point on a door, all the matter of the door starts moving. All right, why is that? Well, many solids have internal forces that resist attempts to change their shapes. Okay? Solids that have these internal forces that try to resist attempts to change their shape are called rigid bodies. So if one tries to stretch or compress a top or a bat or a door, okay, there will be these internal forces that try to resist that, try to prevent that. Now, how are rigid bodies able to attempt to preserve their shape? Well, I'm not going to talk too much about this, but imagine that all the tiny particles that make up a rigid body, imagine that there are stiff springs connecting them. Okay? And how do stiff springs behave? Well, if you try to stretch or compress them, right, they resist that, and they want to stay at their original shape. Okay? Now, there isn't really stiff springs, but there are atomic molecular forces that do behave like stiff springs. We refer to these internal forces that try to help rigid bodies preserve their shape as we refer to them as rigid body forces. Okay? Now I'd like to talk about torque. So I'm going to start with an example. Let's go back to the door that is opening or closing. Okay, so let's imagine that you're looking at the top view of a door with the vertical axis of rotation, with the hinges at the location of the blue dot. All right. Furthermore, let's assume that somebody is applying a force perpendicular to the door at one end of the door. Let's say that that force has a magnitude of 100 newtons. All right. Let's also say that the door has a width, which I will refer to as R. Let's say that R is equal to 0.8 meters. Okay? For this example, the torque which I will denote by a Greek letter tau, looks like a fancy T. The torque is equal to the product of the force applied as shown times R. Okay, so 100 times 0.8, which gives 80 Newton meters. Now, notice something interesting about the formula that I used to calculate the torque. If you applied the same force closer to the axis of rotation, then the R value would be smaller. Okay, the R value, the R variable, is defined as the distance from the axis of rotation to the point where the force is applied. Okay, notice that if R got smaller, the torque value would be smaller. So that means that with the same force, you can cause less of you would have less torque. This is how this plays out in the real world. If you push a door with the same force perpendicular to the door at different positions, you will notice that the door will rotate different amounts, okay, for different positions. The bigger that your R value is, the more that the door will rotate. Okay, try that. That would be an interesting experiment that's easy to do. Okay, now let me show you another example. So suppose a mechanic was trying to loosen a bolt. So I'm going to draw a sketch of a bolt, and I'm going to attempt to draw a sketch of a wrench about the bolt. All right, so this is a picture of a wrench trying to loosen a bolt. So let's imagine that the mechanic is applying a force of 200 newtons to the right end of the wrench, and let's assume that the length of the wrench is 0.3 meters. Okay, so notice that the location of the bolt corresponds to the axis of rotation. Notice that the length of the wrench corresponds to the distance from the axis of rotation to the point where the force is applied. Okay, for this example, the torque is equal to F times R, and once again, let me reiterate that the force must be applied perpendicular to the wrench. If I didn't say that before, I'm saying it now. Okay, so for this example, we would get 200 times 0.3, or 60 Newton meters. Okay, so as I said before, if you apply the force at different positions with different R values, the torque value will be different. Now, mechanics take advantage of this fact. If they have a hard time loosening a bolt, they use what's called a cheater bar, which is essentially a metal tube that they use to put over one end of the wrench to make it essentially they're making the wrench longer. Okay, and then if they pull on the far end of the cheater bar, it's essentially increasing the R value, and all of a sudden they can maybe loosen a bolt that they couldn't loosen before. You see how that works? And it's all because of this torque equation. All right? Now, let me mention one subtlety regarding torques. Okay? The direction, not only does the position that you apply the force matter, but the direction matters as well. Okay? Let me show you why. So looking still at this example of the wrench, okay? Suppose that instead of applying the force perpendicular to the wrench, suppose I applied the force at the same position but towards the bolt. Okay, so I'll put a red arrow pointing towards the bolt to represent the hypothetical new force. Okay, would you agree that pushing the wrench towards the bolt would not help you loosen the bolt? Okay, so note, so the direction matters. Okay, the only component of the applied force that matters for the torque is the component that is, in this example, perpendicular to the wrench. Okay, let me repeat that. When you're calculating a torque, the only force component that matters in the torque calculation is the component that, for like a wrench example, the only component that matters is the component that's perpendicular to the wrench. For the door example, same thing. The only component that matters is the component that's perpendicular to the door. So if you wanted the general formula for torque, okay, it would be best to state it this way. So the F times R that I gave you, that is correct when the force is applied perpendicular to the wrench or the door or a similar object. But in general, here's the formula that I'm going to put in a box if that somehow makes it official. So I'm going to put a little subscript, upside down T, that stands for perpendicular. So the perpendicular force component times R, where R again is the distance from the point where the force is applied to the axis of rotation. Okay? So please keep this formula in mind. All right? And we will use that formula in general when calculating torques.